Ever wonder what a planet spinning in space, a figure skater doing a pirouette, and a simple toy top all have in common? Well, today we're pulling back the curtain on the secret physics of spin, the hidden rules that make the world go round. Literally.
You know, when things move in a straight line, the physics is pretty simple. It's all about pushes and pulls. But the second something starts to spin, whoa, it's like a completely different and way more fascinating rulebook takes over. Let's look at some of the weird questions this brings up.
We've all seen this, right? An ice skater is in a spin, arms out, going at a nice, steady speed. Then, they pull their arms in tight, and bam, they suddenly speed up like crazy. How do they do that? They didn't push off anything. What's going on there?
Or hey, think about something you use every single day. A door. Why is the handle always way out of the edge, as far as you can get from the hinges? That's not just a random design choice, you know. It is 100% based on the physics of rotation.
And then you've got the classic spinning top. How does it just balance perfectly on that tiny little point, totally defying gravity? It seems like magic. So you have a skater, a door, and a top. What's the one secret principle that connects them all? Let's find out.
The answer, it turns out, is in understanding these hidden rules of rotation. And here's the cool part. If you already have a basic feel for how things move in a straight line, you're actually most of the way there.
And this is the big aha moment. For pretty much every rule we know about regular straight-line physics, there's a direct twin in the world of spin. It's like we're just translating the language we already speak into this new, kind of dizzying dialect.
Okay, so this slide, this is basically our secret decoder ring. On the left, you've got the concepts we all get from everyday life: force, mass, and momentum. And on the right, they're rotational twins: torque, moment of inertia, and angular momentum. Let's break these down one by one.
All right, first up, torque. It's a simple idea, really. If you want to make something start spinning, you have to give it a twist. And that twist, well, that's what physicists call torque.
So what is it exactly? Well, at its core, torque is just the spinning version of a push or a pull. A force gets something moving in a straight line, but a torque is what makes it turn or twist, just like when you use a wrench on a bolt.
And this gets us right back to that door handle. See, torque isn't just about how hard you push. It's also about where you push. When you apply that force far away from the center of rotation, in this case the hinges, you multiply its turning power. That's exactly why a little push on the handle swings the door right open, but if you push right next to the hinge, you can push all day and almost nothing happens.
Okay, so torque is what gets the party started. But you've probably noticed that some things are way harder to get spinning than others, even if they weigh the same. And that brings us to our next big idea: an object's resistance to spin.
The fancy name for this is the moment of inertia. And really, you can just think of it as the rotational version of mass. You know how mass is all about an object's stubbornness, its resistance to being pushed? Well, the moment of inertia is its resistance to being spun.
But, and this is a huge but, it's not just about how heavy something is. It's all about where that weight is located. So imagine a solid disk and a ring that have the exact same mass. That ring, because all its mass is way out on the edge, far from the center, has a much, much higher moment of inertia. It's a real pain to get it spinning, and once it is going, it's just as hard to stop.
And this idea, this concept that where the mass matters so much, that is the absolute key to everything. It's the final piece of the puzzle that lets us finally crack the case of that incredible spinning figure skater.
It all comes down to a fundamental law of the universe: the conservation of angular momentum. It's a mouthful, I know, but the idea is actually pretty simple. For anything that's spinning on its own, its total amount of spin has to stay the same, unless something from the outside comes and gives it another twist, another torque. You can move that spin around, but you can't just create or destroy it.
So let's put it all together for the skater. When her arms are out, her mass is spread wide, right? That means she has a huge moment of inertia. So to keep her total spin amount constant, her speed has to be pretty slow. But watch, the second she pulls those arms in, bam, she's crunched all her mass in close to her center. Her moment of inertia plummets, and because the universe demands that the total spin stays the same, her speed has to absolutely skyrocket to make up the difference. It's not magic, it's just physics at its absolute coolest. And once you get this, you start seeing it everywhere. It's why planets keep on chugging along in their stable orbits. It's what makes a gyroscope so weirdly, unbelievably stable. It's why an Olympic diver tucks into a tiny ball to lower their moment of inertia so they can spin like crazy and nail that landing.
Okay, let's bring it all home. What are the big takeaways from all this twisting and turning?
So here's the cheat sheet. You need a torque, a twist, to get something spinning. How hard it is to spin depends on its moment of inertia, which is all about where its mass is spread out. And once it's spinning, its total angular momentum is conserved. That's the secret sauce. If you change the shape, physics demands that you have to change the speed.
And that leaves us with one last kind of mind-blowing thought. Think about a planet spinning out there in the near-perfect vacuum of space. There's basically nothing out there to give it an external twist, right? No outside torque. So, based on everything we've just talked about, will it ever stop? Something to think about. Thanks for tuning in.